So I'll start off with this lecture on exotic primitives. So this is, once again, really just getting you guys familiar with the landscape of what exists. We're going to go over things pretty briefly, and there's a lot more weird stuff out there than what I'm showing. This is just a subset that may hopefully be useful in the near future. So we're going to talk about verifiable random functions, erasure coding, Shamir secret sharing, proxy re-encryption, and ZK proofs. Just a little bit for all of them. So a verifiable random function is used to obtain private randomness that is publicly verifiable. So it's almost like a variation on a signature scheme, where you still have your private and public key pairs, and you still take your input, but in addition to a signature, kind of a proof, you get an output. So how this works is you have, you can sign to get a signature. So this is what this signature in this context means. It's something that other people can look at to check that your output is what you actually said it is. You can also evaluate this VRF for an input with your secret key to get an output, and other people can check that your output was correct by verifying with your public key and the signature to again get the same output that you produce privately. So the output is a deterministic function of the key and the input. So that means that even though we call this random, the verifiable random function, it's actually deterministic. It's just hard to predict. That's what we mean by it's pseudo-random, is you can't guess what your output would be for a particular input before doing the calculation yourself. And in particular, you really can't pick an output you want and work your way backwards to an input that would produce it. So until the VRF is revealed, so when we say the VRF is revealed, until I show other people the signature, only I know what my random output was. And this is an important point in most forms of asymmetric cryptography. Even when we reveal what we're allowed to reveal, it doesn't leak the secret key. So how can this be used? One important thing is that you have to choose the input after the key, because otherwise you could try a bunch of keys in order to change what your randomness is. And then, once you have the setup, the output for a particular input is a random number that's only known to the key holder, and they can later reveal it. So, for instance, you could use this to play a card game in a distributed and trustless way. So in order to draw a card, the players all agree on a new random number X. And then your own card is determined by evaluating your VRF with that input and then mod 52 to turn it into a standard playing card. This way, you now know what card you drew. Other people don't know what card you drew until you publish the signature. And so in order to play the card, then you publish the signature, other people can check it and make sure that the card that you played is actually what randomly you drew. So this is obviously very useful in a transparent environment like a blockchain, because you need ways, or you really want ways, for people to have asymmetric information where you know some secret piece of information, other people know that it's random, but they don't know what it is. So there's a question in the back right over there. And let's see, where are the... Okay, they're both over there.
Hello? Hey, just curious, what do you mean by publish the signature? What is the signature?
Yeah, so going back to the interface, the signature is the proof that other people can use to get your output. So maybe calling it a signature is a little bit overloading the term, but the the order of operations here is the input is finalized, then you evaluate it yourself to get your own private randomness, and when you want to reveal that to other people, you show them the signature, and they can also see your randomness and then take some action based on that. So yeah, the signature is the thing other people can use to check your randomness, your private value. We have one over there on the,
Wait, take
and
it,
the
take it here.
cube's right next to you.
So when you say like verifying, like you said like you can publicly verify, I understand that it's like I can verify that your randomness is really random, or you are verifying something else.
Yeah, that's a great question. So this verify will actually return, it won't just say that it was random, it'll actually tell them what exactly your output is. So for instance, if we decide we're using 10 as the VRF input, I have my public key, you guys all know it. We all agree that 10 is our input. I run this eval and I get my output, and my output is a 1, and we say that's an ace of spades. So now I know that that's the card in my hand. Other people don't know. They know I'm using, we are all going to use a VRF to draw cards. And then later on, I can publish a signature in order to play my ace of spades. And so that's the signature that comes out here. And then you might want to say, well, I want to make sure that you didn't lie to me. I want to make sure that you actually did draw that card, because that's exactly the card that you needed. So what you would do is you would verify with my public key and the signature that I published, and this would give you the output 1. It would give you the same output that I got when I evaluated with my secret key. So yeah, it's not showing that it's random. It's actually other people can calculate for themselves the exact random output that you got. And when I say random, I mean pseudo-random, because it is deterministic.
But so if my signature in a way, so can I verify with the signature and get the number even though the signature that I generated was not random? Like, how can I be sure that it was random?
So you're saying, how can you ensure that the thing was random when the signature is not random? Yeah, so that's actually a good point, because these are, when I say random, I mean pseudo-random. They're hard to predict, and as long as I didn't know or wasn't able to entirely determine the input, so in this usage, how we have, wrong one. Yeah, so the players all agree on the input that they all use. As long as I don't control this entirely, you know that I was not able to control the output of my VRF, of my verifiable random function. We've got another hand in the middle back.
Yeah, Yerbal, thank you. The output in this sense is the hex code, right? That will the signature itself. It's the output, right?
No, so the signature itself is not the output. The output is some random value or pseudo-random value that you get. The signature is kind of like a proof. It's something that other people can check to get your pseudo-random value. So those are not the same thing. This is kind of like a special cryptographic object that can be used in this way to calculate your pseudo-random output.
Okay, and the pseudo-random output is generated by some algorithm that we are not covering, right?
Yeah, exactly.
Okay.
So the inner workings of this eval and verify we're not covering.
Okay.
We have two in the front middle.
Hey, how does this provide a different use case from, let's say, my output is a hash of an input. So I take the input, I hash it, and that's my output, that's my card. Then I create a signature of that, a signature in what we've talked about before. And I publish that signature, and then if someone wants to, if someone doesn't trust that that was actually my card, I show the signature and my card, and I prove that that was it.
Yeah, so you're saying your proposed scheme is in order to get the output, you hash together, what is it, your public key and the input?
Yes.
So if you do that, if you hash together your public key and the input, then if I'm playing against you in a game of cards and we're using this method, I can also hash together the input and the public key and figure out what you drew.
Sorry, not the public key, the secret key.
Yeah, absolutely. You're right. So you could do that in order to get private randomness. That would work perfectly well. You could say that this eval, this is just hashing these two together in order to get an output. You would get a number that nobody else knows. The problem is if you wanted to prove that to other people. Because if you wanted somebody else to do that same calculation, you'd say, oh yeah, I just hashed together my secret key and this input. And they'd say, okay, can I have those pieces of information so I can do it myself? And you'd say either yes and tell them your secret key, very bad, or you'd say, no, that's my secret, in which case they can't check it. So that's kind of the special piece here, is that you use your secret information, yet they can verify with public information.
Right, but in that case, I could create a signature for my hash and publish the signature before, like we did in the previous class with the publish and then reveal. So I could publish a signature. They would have my signature beforehand, and then once I reveal the card, they could prove with my public key that my card is the content, my public key, and they have the signature. They could prove that I already had that card before without revealing the secret key.
Yeah, so that's true. You could do a commit reveal scheme if you wanted to. The trouble is that then you are able to choose what card you drew. Because if you're doing a commit reveal, you're not really using secret information, or I guess the secret information is what you picked as the pre-image of the hash. And so you construct this, or whatever value you're using, you hash it, you sign that, do the whole thing. But you were the one actually that picked the value you signed. So that's the difference, as I understand your question, is when you just kind of do a standard commit reveal, the person doing the commit reveal is picking the value that ends up getting revealed. With a VRF, it's just based on a fixed public input, and then the key pair and the signature used to prove it.
Okay.
So I'm going to build on that because I think so to homogenize both ideas, it sounds like if you had, in this example, control of the input, we're back to square one, what we were just talking about, right? Mm-hmm. So the idea is to either put in the commit reveal, or in this case in the VRF, that aspect in the hands of a known party, somewhere where everybody has access to. So in this case, the input is known by everyone. Yet the single actor doesn't have a hold of it. So to map this in my head, if I had to figure out like an architecture using your card game analogy, I'm guessing players would all have like their own, let's just call it the game client itself, but then have an actual like arbiter server everybody agrees upon to be the one issuing the inputs. And then everybody would then just do the VRF. And that way, at least they know the arbiter isn't cheating. And at the same time, we all can verify that we're just working with that. Is that kind of the mental model here?
It totally can be, and that does work, but there is kind of a little bit of a more distributed way to do it where you're not trusting a single arbiter to be honest. One mechanism that you could use, this is not the only one, in order to have a group of players arrive at this new random number X, and it doesn't need to be too random, it just needs to be random enough, or more accurately, not controlled by one single player, is for every player to do a simple commit reveal scheme and then multiply those numbers together. Because that way, let's say you have 3 players, 2 of them are colluding, they both pick their numbers in a particular way, but they get multiplied together by the third one and they can't predict what the third person will do. So if you are someone playing in a game that's using these mechanisms, as long as you know you're honest, you can trust that this random number was not controlled by anyone else. So it's very feasible to have mechanisms that create inputs that are deterministic from a group, but no one person controls it.
And then that kind of requires several round trips, kind of like what we were talking about the other day with the signatures, where there's a lot more you can do with it, more robustness, but there's the trade-off of having to do several round trips to establish a proper structure.
Yeah, that method that I mentioned does require round trips. I don't want to say for sure, but I'm reasonably confident that there may be one that doesn't.
Probably, yeah.
But yeah, that's just one mechanism. I guess the main thing is you don't necessarily need an arbitrator. You just need to know that this number wasn't controlled by any one person. Yeah.
Thanks.
We've got a few behind you.
You're good. I see that the value in this is producing a random number that you can then prove hasn't been tampered with, it was actually produced in a random way, but I don't understand why you need this secret to do that.
So there's 2 sort of pieces to this, because yeah, it is very specifically you want private randomness that you know ahead of time and then can prove later. And so that's kind of where the secret comes in, is it's only you know it. You have this asymmetric key pair providing information asymmetry where you know the secret, and by the secret I mean this output, before other people do, but you can prove it later. Yet everyone knows it's random. Why exactly do you need the secret? The best answer that I can give is you need this information asymmetry from the asymmetric key pair to produce that.
That makes sense. Thank you.
I just wanted to say something towards his question, basically. And I feel what was missing is that we use this to generate an output which is basically predetermined. So we have the link between the secret key and my identity. And so we only have one role basically, and that's the whole reason we use this instead of the commit reveal we talked about yesterday, right? Just so I get it.
Yeah. So that is a true and important point, is that because your public key is known, if you're using one of these systems, you want your public key to be known by participants. Like we have in this usage slide, you need to choose the input after the key. So your key is known, it's linked to your identity. Once the input is selected, the output, you can only ever produce one. It can only be the one specified by this VRF. So you're kind of locked in once other people know your public key and the input goes. You either can, if you're, let's say you're playing this card game, once the input is created, you're locked in. Everyone knows, including you, that there's only one random number that you saw privately. If you choose to not show your signature, you say, oh, I'm not going to show you guys, I don't want to. In most situations where this is used, other people can just assume the worst, and it ends up working out pretty well from a security standpoint. So that linkage is very important. If it was just, you have this input and then you come up with a key and then show your randomness, you could just pick a bunch of different keys until you get the randomness that you wanted. Over there.
Hello. Where's the entropy introduced for the generation of them?
Where is the entropy introduced? So the place that the entropy is introduced is where this number is not controlled by any one person. Is there new entropy other than that? No, because it's deterministic and pseudo-random. So we're not actually having true entropy. But importantly, the way to go from this, random number to the output is one way. So you can't really easily go backwards. But more importantly, yeah, as long as for you as a participant, there's randomness in that number, you can't control what's going on. If for you as a participant, you're able to choose that number, then you can basically pick whatever output you want, given a long enough time to calculate. I think one there in the center, a little to the left.
Behind you. Behind you.
Okay, these cubes are getting more dangerous and dangerous. So if I essentially understand, a third party has to provide the randomness, and then, or some library or something like that, or who is providing the randomness? Because
this randomness here.
yes.
It depends. It really varies. So so maybe in this case, one thing that could happen is you could use the commit reveal from every participant and then multiply the numbers together, like I described earlier. Another place that this could come from is maybe before you actually start the round of cards, you say, all right, this input will be like the exact ticker price of this stock at this specific time. The participants can't control that exactly, assuming it's a low stakes thing. And that way, you also get some randomness. If it's in a blockchain situation, you could say, okay, the input will be the hash of this block number. Can't control that either. So the randomness could come from many different places, or the unpredictability could come from many different places. And as long as one participant does not completely control it, this works, and you can trust that they didn't know their output before the input was committed to.
And another question to that, you produce the signature only once, right?
Yes.
Okay.
And there's one right behind you.
Awesome. Hi. Can you go back to the interface, please? So it's stating the verify function is getting the private key, the signature, and optionally outputting the output.
Yeah, this is actually stands for public key and then the secret key.
Yeah, so verify public key, signature, option output. So isn't it also supposed to put in the input as well? Because there will be, during like a playing card game, there will be multiple signatures from a player. So it's not like referencing the input at all. So if I just give you like a signature I'd done before for a previous input, it will reduce the same output. So I draw an ace and I just give over the signature for an ace. So it's not, is there somehow the signature tied to the input? I think the input is missing there in the verify signature, as function signature, isn't it?
I'm actually not entirely sure about the specifics. That is a really good point. It's possible that the input is kind of encoded in the signature. It's also possible that I omitted something here, and it should actually be public key signature input.
I guess.
So I will get back to you on that, but that's a really good point. Could be either one of the two. I'm not sure which.
Okay, thanks.
Okay, cool. Where was I? So there are also some various extensions to VRFs. So there's something called kind of a threshold VRF or common coin. So this generates the same random number for some number of the participants if a certain threshold participate in the VRF. There's also ring VRFs where the VRF output could be from any one of a number of public keys. So this is very similar to ring signatures that we discussed, where you see the signature and you say, well, this could have come from any number of public keys. Maybe, it's a group of 9 and you don't know which one out of the 9 it came from. This same thing with a ring VRF. So one thing that is still important with these ring VRFs is you can still trust them in the same way. A participant in a ring VRF can still only output one random number. The mechanism behind how it works is out of scope, but it still works in the same manner where you can trust that the randomness was fixed for that individual. So now we'll go into erasure encoding, or erasure coding, also called error correcting codes. So this is basically magical data expansion. We turn data into pieces with some redundancy so it can be reconstructed even if some parts of it are missing. So we can turn a message of K symbols into a coded message that's longer than that of N symbols, but we can recover it from any K of the N symbols. So what that maybe means is if I have a message and it's 3 long, I could turn it into one that is 5 pieces long, and then any 3 of those 5 pieces can be used to completely reconstruct my original message. So to give a little bit of intuition on how this works, it mostly depends on both parties having an understanding of what types of messages are valid using this code. So imagine you're receiving a message and you know ahead of time the only possible things that you could have been sent is either the word file or the word ruin. You don't know which, but you know it's one of those two, and anything else, something happened to the message. It must have gotten corrupted in transit. You're not so sure. So how would you think to yourself, how would you classify each of the following words if you received it? Which one of the possible words do you think it would be? So if you receive pile, do you think originally someone tried to send ruin or tried to send file? Well, probably you would think this actually was originally file because just the P changed to an F and you get what was sent originally. Now if you have pale, this one probably you see, okay, how many characters do I need to change? What's the distance from file? What's the distance from ruin? And it's closer to file. And you can apply this same logic to all of the words that you received. This isn't the only way to do it, depending on how you think it might be corrupted. But you kind of see how close are these things that I received to something that's valid. And this also means that we can find the errors and correct them that were in these messages. So like in this message, we know what the errors are. The errors were this P and this A. This should have been an F and this should have been an I. This is kind of like roughly how error correcting codes are actually working. But of course, when you're sending real messages, they might be very similar to each other. So if you have, message 1 or message 2, can you apply the same technique? It's not necessarily so easy to separate them. Like what if you received message 3? It's only one character off from both of those possible inputs. And so with these codes, we magically through cryptography extend these messages uniquely to the message that was sent so that they're different enough that when we receive something that has some characters missing or some characters wrong, we can figure out which one it probably was. So hopefully this explanation gives a little bit of intuition on how the erasure coding works. But in the end, it boils down to we have our original data, we add on more stuff, and even if we lose some of that stuff later, we can still get back the original message. So in their classical use, these are typically used for noisy channels. And actually, erasure coding and error correcting codes are used at every single level of really how every single computer works. Like they are used when you're reading bytes from a disk internal to the disk's hardware. They'll be used when you're transmitting bits across a lossy channel. They'll be used in all sorts of places. And when they're used in these cases, we just want to correct for a few bits of the original data being randomly flipped. So typically, that means that we're not expanding the data by much. We're maybe expanding it by 10 or 15 or 20% so that we can account for a few errors that might occur. In a decentralized system, we might have data that we want to keep publicly available. So let's say the block data for a blockchain. We want to keep it publicly available, but it's a little large. We don't want to send it to 100 different people and tell all of them, you have to store a full copy of this data. So what this is kind of an efficiency gain if we use some error correcting codes. So we don't necessarily trust everybody who's storing pieces, so we use a very, very large encoding. We make n much bigger than k, and that way, even if some people lie about their pieces, they don't provide their pieces, we can still reconstruct the original data, but each individual participant doesn't have to store as much. So are there any questions about error correcting codes? All right, we got one in the back right.
Which one? Oh my God.
Thanks. So does that mean that the amount of pieces of n is always going to be less than k by like a significant margin?
Does that mean that the amount of pieces of n is always going to be less than k?
That you need to recover k.
Ah, okay. So, no, you always need, going back to the definition, so if you start out with a message of k symbols, you still always need k symbols in order to recover it. However, you get this coded message n that's much larger, and you split that up and distribute it out. And you only need to receive k of them back in order to recover the original message.
Gotcha.
And one thing that I'm going to remind everyone that I have not been great about enforcing either, but again, please say your names before you ask a question. Throughout the academy, the instructors rotate, and so I'll be gone after today. And the next instructor won't know your names at all. So please continue saying your names before you ask a question.
Hi, I'm Viviana, or call me Vives. So I didn't fully, I'm not sure about the use case. So it's obviously for like noisy channels, but like we don't have that yet, that in blockchain, right? Or do we? And like then you said that is that, so in that case it's like everybody stores a little piece, and then some people or some actors disappear, and I have to recover for those pieces. Will it that?
Yeah, that's exactly correct. Okay, there's a few over here. Woo!
Sorry. Okay, Julian. So you're taking K and you're making more ends. How do you know what to make redundant? Because you don't know what you're going to lose over. So like, are you just making double and making sure you have everything?
Yeah, so that's a great question. Error correcting codes are actually really cool because they are much smarter than that. That is something that you might try to do. You might say, okay, you know, I have a group of 10 people. I have 5 pieces of data that I want to replicate. So what I'll do is I'll just split it into 5 parts, make 2 copies of each, and then I'll hand person 1 the first piece of data and person 2 the second copy of that part, and do the same thing on through your group of people. If you do it in that manner, it actually only takes 2 people being malicious in order to lose part of your data permanently. Because if person 1 and person 2 decide to not give back the data, then you've lost all copies of the first chunk. So the really special part about error correcting codes is that you can recover it from any K of those n symbols. So you don't need to worry about which participants are malicious, you just have to worry about how many. If you were doing that same example where you have 5 pieces of data and you share them with 10 individuals, or you have 1 piece of data and sharing it with 10 people, and let's say you split it up into 5 chunks, but you've extended it, so K is 5, N is 10, you split it up over those 5 people, any 4 of those people, or really any 5 of those people, could be malicious, could give you wrong data, could not return the data at all, and you could still recover the original message. So yeah, it doesn't matter which set of people you give redundancy to, because everyone is, has some redundancy in this system.
Yeah. How much can we reduce? How much can we reduce the size of the original data with the error correcting code? Which is the limit?
Yeah. So how much can we reduce the size of the original data with these erasure error correcting codes? So there's a little bit of nuance here, because in terms of reducing the size of the data, you're actually increasing the size of the data. You're adding more pieces onto it. And, even if let's say you extended it and then dropped everything you didn't need, you would still end up with your same size data, just K symbols long over here, K symbols long over there. So when you have just the single, if you're doing it to store yourself, you're increasing the size of your data. However, if you introduce specific assumptions on what percentage of participants in your protocol are dishonest, then you can reduce the amount stored by each participant. So for example, if your protocol says 1/3 of people may be malicious, and I want to deal with that, then you can split up your data into enough pieces and distribute it in such a way that each person is storing much less than the original, but we still have enough redundancy to account for that 1/3 being malicious. So it really is only when you introduce specific trust assumptions that you end up really having those data storage benefits. Because if you're just storing it for yourself, you are actually storing more data than original. Yeah. And actually, one thing that is maybe an important comparison there, if you trusted everyone in your protocol and you wanted to split up the storage, it would be more efficient than adding this redundancy still. So if you have your data and it's 10 pieces long and you trust all 10 people in your group, they each store one piece of data, or length one of data. Whereas it would be different if you maybe trusted only 50%, and so then you're having each person store twice that much data. They're storing 2 parts of the data. Yeah. Got in the front middle.
Kelvin, so you kind of alluded to this with your final answer here, but I'm just looking at this in terms of what is sort of we're expanding data and then we're sort of filling in gaps. So what's the sort of complexity, right, that we're looking at here? This doesn't seem like a trivial operation that you can run in like order 1 speed or anything. And it sounds like people are going to spend a considerable amount of time. Even though you can answer that question directly, what I'm trying to probe for is what are the trade-offs? What are the weaknesses here?
Yeah, so what are the trade-offs here? Error correcting codes are actually shockingly efficient. The math that they use under the hood there's ways to do it pretty quick, quicker than you might expect. Can't give numbers because I don't have them off the top of my head. There are trade-offs in the sense that you're storing more data, in the sense that you're paying for this encoding and decoding. But for the most part, that's the only thing that you're trading off. It's a bit larger, you pay a little encoding cost, you pay a little decoding cost, but overall this is a pretty rock-solid foundational technology that doesn't actually have many drawbacks. So there's one more in the, okay, you already have a speaker, or a mic.
I'm Dheeraj. I assume the input for this method is bytes. So can we also split the private key and seed in multiple parts and recover if some parts are gone?
So that's a great question, and I'm actually just going to take that opportunity to move on to the next slide, which is Shamir secret sharing, because it's very similar to what we just discussed. So this is turning data, typically a secret, like you said, into pieces so it can be reconstructed from some subset of the pieces. So you turn a secret into n secret shares, and then you can recover it from any k of the shares. When you start this protocol, you pick what n is and you pick what k is. And really, you can do this for pretty much any, this many out of this many. So you could do it for 3 of 5, you could do it for 5 of 7, you could do it for 2 of 9. You can really choose on your own how you want that to work. The important thing that's slightly different, not necessarily, overall Shamir secret sharing is very, very similar to the thing I discussed previously. K-1 shares, so if you have 3 of 5, only 2 of the shares, having those together reveals nothing about the secret. You don't know anything about what it is. So that's the important part, is that you only if you have K of the shares can you get it back. Otherwise, it's as good as if you had nothing at all. So Shamir secret sharing is a very similar thing. Here's kind of a diagram of a little bit of an example. So this would be a 2 of 3 scheme. So you can see that any pair of these participants, if they put together what they know, they would receive the whole key. But any one of them doesn't necessarily know what's left. They don't know enough to construct the whole thing. It's not fully representative, but it's close enough. So pros and cons of Shamir secret sharing are also pretty simple. The pros, you can reconstruct a secret if you lose it. And the participants, if they don't get enough shares, don't know anything about your secret. The cons, so can anyone else who collects enough shares. So it really, with Shamir secret sharing, what you want to do with it depends a lot on where you're placing your trust and how much you care or how much you believe that those locations will not collude or will not become vulnerable. So it's mentioned, you may have heard of it before. Some people choose to use this by perhaps having their secret and they decide, all right, I'm going to make it a 2 of 3 and store these 3 pieces in each of the 3 major cloud providers in the assumption that they will not be colluding. Some people might do this by sharing it with friends that they trust and maybe having a higher number of shares that need to come together in order to reconstruct it. Maybe not even telling each person they're giving a share to who everyone else that owns one is. So there's a few different ways to make use of this primitive, but fundamentally it just breaks down into you have a secret, you get the shares, you pick how many you need to reconstruct the original. You got a mic already, Kelvin.
Yeah, got a mic here. Kelvin again. So I don't know, some of us might recall that one time when Vitalik got a mass dump of like Shiba Inu on his account, and one of the things he panicked about was he actually didn't have his secret key on him because his family had the other half of his secret key, and it was like cold storage and everything. He had to guide his mom to do some things. That's not essentially Shamir's secret, but he basically split his key in 2. First half he had the other one, and so on the other one. So like when you can resort to little like crafty things like that, I'd like to know what leads people over to Shamir's secret, and if I had to answer my own, is that n is arbitrary number of shares, whereas with doing that sort of clever thing, it's only as long as your key is. You can only make as many keys sub the length of your shares sub the length of your key. Is that kind of a reasonable rationale?
I'll say that if you're just trying to split up a secret, doing it with Shamir secret sharing is as good as anything else. There's no reason to use something else. It's very possible that example you gave was using Shamir secret sharing. It's just that it became 2 of 2. There are some other clever things that you can do around key splitting depending on the underlying cryptography. There's kind of a mechanism that you can construct with certain forms of cryptography where you split a key, or you basically have a key that's in 2 parts. And so if you want to do an operation like signing, you can do it with the 2 parts separately without ever combining them into one secret key first. We're not covering this, and I don't know too much about it, so I'm not going into it in depth. But there are other mechanisms out there that might be more appropriate depending on your use case and what you think is secure. But if you are just turning a secret into many parts and you want so many to be a threshold for recovery, there's really nothing better than Shamir secret sharing. And we got one right behind you to the left.
Yeah, I think there's a challenge on, so out of the 24 keywords, how many keywords can you reveal so that others are able to crack your wallet? So if Vitalik sort of gave away some keywords to his family, it's very weak security in a way. Okay. But yeah, in terms of like this, it sort of makes sense where you sort of give away info and yeah, so nobody will be able to crack that.
To elaborate on that, if you, let's say you had like a 32-byte key, and you decided that instead of using Shamir secret sharing, you think it's kind of dumb, you're going to do your own thing, you're just going to take the first 16 bytes and the second 16 bytes and distribute those. If a participant is malicious, well, the one other participant, they now know half of the key, and if they wanted to brute force search, it would only be 16 bytes they have to figure out instead of 32. If you instead use Shamir secret sharing, it would be the full 32 bytes that they would have to search, the full brute force space. And this gets even more extreme if you were splitting it into more pieces. So if you're doing maybe like a 4 of 5 threshold, then if you just cut up your secret key into 5 parts, distributed those, if you only had 3 of them, you would only search for 40% of the length of the key in terms of entropy, whereas with Shamir secret sharing, you don't have any information. It looks like Nuke has something that he wants to say in the aisle there.
I can't.
Yeah, I think that's a really important point and reemphasizes this concept of don't roll your own crypto, right? In the sense that if you try and come up with fancy ways in which to share your secret, you can, for example, here, a not so simple way, or a very simple way to just split it up, you're actually exponentially making your security worse, the more of it that you're passing around. But with Shamir secret sharing, and maybe Nate can confirm this, right? Sharing those key shares is not fundamentally corrupting the security of everything unless all of them come together to that threshold level. So it's all or nothing at the threshold, as opposed to some of these other mechanisms where you might actually be leaking and weakening the security overall.
Yeah, that's exactly correct.
Can you please expand on that? Because if you go to the previous slide, for instance, I think so
the
for me,
image?
yeah, this one, for instance, you have here, for instance, if you take this graphic, I have the impression that the part of the key it's leaked.
Yeah, so that's why this is not a super accurate rendition here.
Right.
The trouble is that in order to have an accurate graphic, it would have to be just like a chart of polynomials, which is a little bit less intuitive than a picture of a key.
Just for me to understand, so basically, Shamir secret sharing, I just assume it's a black box, and the key -1 reveals nothing. That's the way to go with it.
Yep, that's exactly the way to go with it. Yeah. No, it's a hard thing with diagrams for both this and also back on erasure coding, because it's hard to visually show the underlying mechanisms in a way that makes sense. Like that's why we kind of have this puzzle piece in the middle completely opaque, because you can construct from any subset of it. It's a little bit hard to diagram. Yeah, but you're totally correct. For many k-1, you don't get any information, and this is not super accurate in terms of what information actually goes into the shares.
Thank you.
All right, we got one more at the back right.
Hi, is there any minimum value for k, like minimum percentage of n for k value?
Is there any minimum value of k?
Yeah, say any 10 shares, what should be the minimum value for k to get to reconstruct the total key?
So are you asking when you're choosing n and k, is there a minimum, or are you saying what is a good choice for k?
I've already chosen n.
Yes.
So what should be the minimum percentage of k so that I can reconstruct back the entire key?
Okay, so when you construct this scheme, you get to choose both n and k.
Okay.
So you could, for instance, if you choose n to be 5, You could, in theory, you could pick K to be 1, in which case you're not really using Shamir secret sharing, you're just spreading out copies. But you could pick K to be 2, 3, 4, or even if you wanted, you could pick it to be 5.
Okay, it's the developer choice.
Yes. Yeah.
Got it. Thanks.
One more over here.
I try to make link with all our knowledge. If I understand the Shamir secret sharing, we can like put transaction with like a key we construct with that scheme. So it's more of like the multisig wallet, the multisig signature. Is there like relationship between them?
Yeah, so that's a good question. Kind of what's the relationship between Shamir secret sharing and a multi-signature? So the big difference here with Shamir secret sharing that maybe I didn't make super clear is if you want to do anything with, supposing that this data is a secret key, if you want to do anything with that secret key, it needs to be reconstructed with K shares, and then it's all in one place. So when you collect the shares to a certain location, that location has the full secret key. And so you can't do it without having one place you trust to have that secret. So in the case where it's your own key, you spread it out for recovery purposes, that's totally fine because once you've regathered the shares to yourself, you wanted to know the secret in the first place. If you're doing it with a group of people who doesn't necessarily trust each other, it is true that you would need to come together in order to construct a signature. But once you did, one person at least would need to know the full secret key and could then continue to do other things with that knowledge. So there is kind of a fundamental difference here in terms of trust assumptions about the group as a whole, where this Shamir secret sharing, when you construct it, 1 point of trust. When you reconstruct it, again, 1 point of trust. With threshold multi-signatures or just general other multi-signature schemes, the trust can stay distributed. At the point of secret creation, you can have a distributed key generation protocol. So again, not 1 point of trust. And then at the point of like creating a signature, also not 1 point of trust. So yeah, that's a very important difference here. Is generally you need the multi-signatures for a group that doesn't trust each other. Shamir secret sharing for recovery of your own secret is the most common use case. All right, great. So now I'll briefly mention proxy re-encryption. So this is something that lets you create keys that allow a third party to transform encrypted data so someone else can read it without the third party being able to understand. So if you have Alice is the owner of this data, has encrypted it, and sent it to the proxy for storage. Alice can then create a key, a re-encryption key, give it to the proxy, and the proxy can re-encrypt the data so that Bob can read it. Bob can decrypt it, but the proxy isn't able to decrypt anything. So kind of, it might be a little bit clearer looking at what an API for this might look like. So you can encrypt data to yourself by using your public key and a message, and that gives you a ciphertext that you can decrypt. You can decrypt data. Oh, that's actually a typo there. That should be going from ciphertext to the message. Let me fix that super quick. Okay, so you're going from your ciphertext to the message. And so again, this is if something is encrypted for you, decrypt it with your secret key. You can make a re-encryption key using your secret key, their public key, and returns something called a re-encryption key. And this can be used to make something encrypted so you can read it into something encrypted so that public key can read it. And then finally, this is the thing that the proxy would do, is they can re-encrypt using a re-encryption tree some old ciphertext into some new ciphertext so that the new person can read that. So a super classic type of use case for this would be if you want to store some data in the cloud and then be able to authorize others to access it without having to download all the data yourself, decrypt it, encrypt it, send it over. So in that case, these Alice and Bob would still be the participants. The proxy might be a cloud service. And when Bob wants to access the data, talks to Alice, says, hey, can you send me a re-encryption key? And then gives it to the proxy, and the proxy is able to re-encrypt the data so that Bob can see it. It's kind of like an authorization scheme. So yeah, questions about proxy re-encryption. This is the last slide on it. Super brief, like I said. There's someone in the center on the right.
Hey, Julian, is this how Arweave works? I don't know if you...
Is this how Arweave works? I'm not familiar with it, so I can't say. If they have this type of mechanism,
It's like
very possibly.
It's distributed storage, so in some way.
Maybe. I don't know. Yeah.
Arweave doesn't work that way. Arweave is everything is public. Here, the data is encrypted.
Okay.
Yeah. So this looks really interesting. Can you go more into details how this works? Like, what happens? How can we do that magic? Like, how
yeah.
can the proxy basically decrypt the stuff and then the Bob can read it? But like, what's going on? Thank you.
Yeah, so that's a good question. As far as I'm aware, at least one version of this proxy re-encryption uses BLS cryptography for the asymmetric key pair. There's multiple different implementations. There's papers on it. I don't know about like production level libraries and implementations, but proxy re-encryption is what you want to search to find more information on this. I can't go super into depth in it because I don't know super in depth in it, and I don't want to give you false information. Front, pretty much in the middle.
Hey, Facundo. So, is the re-encryption key, you, as far as I understood, you send it through a public channel, right?
Yes.
So it's public knowledge.
Yes.
If you're constructing that re-encryption key with your secret key and that other person's private key,
public key.
Public key. Could that re-encryption key be maliciously used by that person, so the owner of that public key, to re-encrypt another secret that you have, but you didn't want to give him access to it? And so let's say that you have two files.
Yeah.
You're trying to give him access to the first file, so you publish this re-encryption key. The owner of the other public key grabs that re-encryption key and uses it to re-encrypt the second file, which you didn't want to share.
Yeah, my understanding of this protocol says, yes, that is a concern, and you need to consider that. One thing that does mitigate that a bit is that you do have the proxy who actually has to do the re-encryption, or more importantly, the proxy is the one who has access to your encrypted files and is able to send them over to Bob. Otherwise, Bob doesn't know them anyways. So with some carefulness in terms of Alice telling the proxy which files to send to Bob, that can be mitigated. But that is an important thing to note is, yeah, if you send the re-encryption key to Bob and then Bob gets a hold of something you've encrypted with this scheme, Bob can decrypt it. Yeah.
Okay, thanks.
Okay. So now I'm going to go a bit, but not too much, and we will go more into it later in the course, well, more into how it's applied into ZK proofs. So ZK proofs stands for zero knowledge proofs. It's how we can do private operations on a public blockchain and have everyone know that they were done correctly. So what does a ZK proof look like? It's when a prover wants to convince a verifier something is true without revealing why it's true. These can be interactive protocols. Interactive protocols meaning that you need multiple rounds. Perhaps you have conversation back and forth between the prover and verifier before the verifier is finally convinced. But for the most part, we'll be talking about non-interactive proofs. Non-interactive just means it's like a normal proof. You can verify it offline. You don't need any extra input from the prover. So what can you actually show with a ZK proof? You can actually show any NP relation, a function from a statement and a witness to if it's true or not. What does that mean in terms of, you know, a developer and engineer? Mostly it means you can show pretty much any computation. You can prove that anything was done correctly, or you know some piece of secret information to do something. So again, just to reiterate, you're saying that the prover knows a witness for this statement, and they show that they definitely do know it, but they don't tell you anything about the witness, about what secret thing they do know that allows that to be true. So the interface overall is you have a NP relationship from a statement and a witness to a Boolean. You can prove a statement and get a proof, and then you can verify a statement with the proof and get out whether or not the proof was valid or not. So one thing that is actually an example of a ZK proof is creating a signature. So by sending someone a signature over a particular piece of data, you can show that you know the private key without telling the private key. And so the statement in this case is the public key, and the witness is the private key. Well, more specifically, the statement is that, you know, you're able to, well, that you know the private key corresponding to the public key. The witness is the private key. One way that this could be an interactive proof, if we were talking about that, is I say, I know the private key corresponding to this public key. And someone says, prove it, sign this message, and send some random message. And then in response, I would produce the signature. And they would say, all right, based on the cryptography, there is a 1/2 to the 256 chance that you did that by chance. So I'm convinced. If it was a lower probability, they might go back and forth multiple times saying, prove it for this, and you prove it for that, and eventually decide, all right, I'm convinced. So going even further than ZK proofs, you have ZK snarks. So what that stands for is a zero knowledge, succinct, non-interactive argument of knowledge, which is quite a mouthful. So we'll break it down into pieces. Zero knowledge means that it doesn't reveal anything about the witness that wasn't revealed by the statement itself. So one thing that is a little nuanced in zero knowledge is what specifically is hidden. For instance, with this Schnorr signature example, the information that we're using Schnorr signatures, everyone knows that. The cryptography behind it, that's also still all public knowledge. The public key that the statement is for, that too is public knowledge. The only thing that is hidden is the private key. So again, that's what it means by nothing that wasn't revealed by the statement itself. It's nothing that's not known by the context, by the problem that's being proven. Succinct means that the proof is small. Often with ZK snarks, the proof is almost unbelievably small. And then the proof of knowledge is basically saying you're proving that you know something in particular that you're not revealing. So if you can compute correct proofs of a statement, then that also means that you're able to construct a witness. So again, with ZK snarks, we can show any NP relation. So again, show that you know it without revealing anything about it with a small proof, even if the witness is actually quite large. What can we show? Again, every NP relation, and a lot of things can be encoded as NP relations. If you've heard things about, arithmetic circuits or, constructing ZK circuits, that's kind of doing that step of, here's a thing that I want to talk about, and I need to get it into the form of an NP relation in order to use this ZK snark or just standard ZK machinery. And another thing with ZK proofs is that they can be used as a sort of scaling solution, because you can have a small amount of data, because again, snarks are succinct, which is the ZK proof, and then some execution time in order to show properties of a much larger data set that the verifier doesn't even need to know. So these are really, really complex and also really magical. It's really crazy that this is possible, and it almost is hard to believe. I'll take some questions now, and before I answer questions, let me caveat it by saying that I am not super knowledgeable on ZK proofs. It's a really deep field. I'm happy to point you at resources that go a lot deeper under the abstraction barrier than I'm going here, but there very possibly will be a bunch of questions that I can't answer, unfortunately. So I'll start with, there's 3 questions in the front middle right here. And there's a box coming from in front of you.
Can we get a real-world blockchain example for ZK?
Can I give a blockchain example for ZK? I think I've got one right here. So one way that scaling can be done with ZK proofs in a blockchain is if you have a large amount of data, for instance, like the entire database of a blockchain, and either you're verifying on like a mobile phone or you're verifying on another blockchain. So on that other blockchain, it's very expensive to have data there. It's very expensive to do a large amount of computation there. That's how you can have what's called a layer 2 blockchain using these ZK rollups, which are basically ZK snarks. Basically, what that means is you compute a proof of validity that you did in fact construct your layer 2 block correctly, make it very small, very fast to verify, and post that to a different blockchain, and the different blockchain checks that that is correct, that the proof is correct. How exactly that works, the details, the different mechanisms, which ones exist, we'll go into that much later in the academy once everyone has the appropriate background. But that's the basic scheme.
My name is Victor. I don't really understand what an NP relation is, I think.
Yeah, so what an NP relation is I mean, I can give the definition, which is it's something that takes non-polynomial time to compute.
Alright, so it's related to the NP class.
Yeah, this is like P versus NP classes of problems. For me personally, I find that it's not super intuitive what that really means in terms of actual problems. And so I like to think of this, and you can pretty accurately think of this as you can do arbitrary computation in these ZK proofs. And that's what it means by you can do every NP relation. There is more depth to it and more nuance, but that is pretty accurate way to think about it.
Perhaps my guess is that there exists like an a reduction to a problem, an NP problem, for example, like a 3-call or set, the Boolean set stability, and the other one is like you have to color, maps, well, such that the color of a country is not the adjacent colors are different, and those problems are equivalent, I think, to these ones. I think that's my guess what it might be referring to.
Yeah, I believe that, and again, this is from what I remember, I believe you can reduce every NP problem into every other NP problem, and that's been proved in theoretical computer science. And that, yeah, generally what people are doing is they're taking their problem and they're turning it into some, circuit solvability or like SAT or whatever. They're turning it into that type of problem and then using a ZK proof to show that it was correct.
Right.
Yeah.
Thank you.
Wait for the mic real quick. And say your name.
What I'm saying is, what I've been studying is that the set of the NP problems are a subset of the Seiki type of problem.
You said the set of NP problems is
a subset.
A subset of
Seiki problems.
Say.
Zero knowledge problems. Zero knowledge set, complexity set. No, it's a mathematical thing. No.
I'm not familiar with that. I can't give you, I don't know the second thing that you referred to, so I can't say anything. Or maybe I do, and I'm not matching those together right now. Yeah. We got another hand right there.
Jacob, the thing that I don't understand is how this works with the halting problem, because the halting problem discusses how a program cannot prove the end state of another program, but this seems like you're doing something very similar to that.
That is a good question. So we know that the halting problem is unsolvable. You can't prove whether or not, or a program cannot prove whether or not another program will halt necessarily, without executing the whole thing, which potentially never halts. How does that fit? It seems like this is impossible. Another great question. I don't know specifically how these ZK snark, NP relation provings actually relate to the halting problem in particular. I do know that most general computation can be done with ZK proofs, but that is a great question, and I don't have a good answer for it. Somebody else in the class may possibly have an answer for it, so if you do, raise your hand really high. All right.
Okay. Rather here. So this one is actually verification, right? So for NP, the verification is polynomial time.
Yeah, the verification is polynomial time.
Yeah, but what he was asking is the actual problem itself, I guess, which is in NP. But yeah.
Yeah, I think, my understanding of it is that P and NP complexity classes are separate from, the halting problem, or something is computable. It's called the theory of computing recursively or recursive. And I think, so the reason this is related, I believe, to P and NP complexity classes is one-way functions. So a one-way function, like computing it is P and verifying it is P, but reversing it would be NP, right? So it's... Yeah, so I guess we use zero knowledge proofs, like the way zero knowledge proofs are related to P and NP complexity classes is that you can prove something quickly, right, in P time, but you could not reverse that. Like you cannot know anything about the witness, right, which would be a very expensive non-polynomial computation. I think that's why it's in the complexity class NP, and it could be reduced to an NP complete problem.
Yeah, I really wish that I could give better answers to this, but unfortunately, this is the one thing that I'm not super well versed in. It's a very recent field. It's a very deeply complex field. I don't know if you remembered the scary equations slide that I showed, like the very first slide, that huge box of equations and flowchart and whatnot. That's from something called bulletproofs, which is an implementation or one form of ZK proof scheme. So yeah, very complex. I wish I could give you guys better answers. Unfortunately, I don't know a huge amount of depth in ZK proofs. I know what they are. I know how they're used, but I don't actually know how they relate to these deeper questions.
not as deep of a question, but so these can only be used for NP complete computation, not NP hard computation?
My guess would be yes, because I assume it has to be, well, I assume if it is NP hard, then it would be very hard to prove. That would be my best guess, but again, I haven't really looked into how those two are connected, so I don't know.
Thank you.
All right. Thank you guys for the grace. I'm doing my best. And again, if you have more questions, there will be later in the course a lecture by Sophia Gold, who knows way, way more about this and all the technicalities for it. I think the lecture is on blockchain scaling solutions. Maybe, I'm not sure which week, but definitely save those questions, write them down. If you want to ask them, you very well may get an answer at that time. Okay, so we went over those, so how we use them for scaling in blockchain. So for privacy, with ZK proofs, a user can have private data, but we can show publicly that the private data was used correctly without revealing that private data. So an example is with like a private cryptocurrency. We can keep who pays who secret, and we can also keep the amount secret, but show that they're still positive. So this way there can't be bad transactions because of course the amounts are all still positive, but you keep a lot of privacy in terms of who has what amount of money, who's paying who, what's going on in this blockchain. You keep a lot of things private with these ZK snarks. However, this is very hard. Again, like it's both hard cryptographically, it's also hard on a protocol level to make something like this work, because you really have to think at every step of the way, how are we making sure that this thing is operating in a private manner, and how are things coming in and out of this without revealing anything about themselves. Yeah, so in terms of practical considerations, this is obviously an extremely powerful cryptographic primitive. You can do crazy things with this that are really unbelievable. It can be useful for both scaling and privacy. And one thing that's worth noting is oftentimes when you have sort of like layer 2 type chains, they're using this type of like ZK snark roll-up approach. They don't care about the zero knowledge one bit. They don't care about it. They're just using it for the scaling alone because it's still that powerful. And then again, you can design many protocols using ZK proofs that just would not be possible otherwise. The downside is that it takes a long time to prove this for general computation. So what that means is it's very fast to verify a proof once you have one, but it can take a really long time to actually generate a proof and a lot of computational power. So in order to be fast enough, typically you're going to need to hand optimize this. What does that mean? Typically that means how you're transforming your computation into this NP problem. You need people who are experts in this in order to do that. Again, this has a really weird computation model because you're doing this transformation from your problem, which is in normal, presumably like normal code, turned into this non-deterministic arithmetic circuit computation model. So again, not many people are familiar with it, and you need really experts to make it fast enough to be practical. So and again, this is from 6 months ago, so things change very rapidly. But if you want to use this for one thing, expect a team of skilled people to work on it for probably a year. If you're watching this later, so you're not, but if you were, it's very possible that people will have built tools to make this less painful. You already see that now. There's tons of innovation in this. It's a very new field, and so it's progressing quite quickly. But at this point, if you want to use it, you need people who are skilled in it, and it's going to take some time. Huh? Is this substrate? Not yet. I don't want to, I know that there is work being done in order to get ZK proofs into substrate in some form. I don't know where that's at. but it's probably in the works. So in terms of some of the things that go into this cryptographically, you need special hash functions that are zero-knowledge friendly. So those will still, then one great thing about the way that you guys have been learning this is you've been learning the APIs. You know what a hash function takes in, what it spits out, and what properties it has. Those will still be the case for these ZK-friendly hashes. They'll just have a different name. Additionally, you might be using some non-hash-based data structures because, again, you want something that's a little bit more ZK-friendly. So that could look like RSA accumulators or maybe be polynomial commitment-based. So a polynomial commitment is kind of like a hash function on steroids. You can have one small piece of data that is a commitment like a hash to many different things. So you can use this polynomial commitment to commit to a bunch of different statements. So that's zero-knowledge proofs. Again, like I said, if anyone wants to go deeper into it, definitely we can recommend great resources for learning this from the ground up. They'll go much, much deeper, way below the abstraction barrier that we've tried to keep. And even Berkeley, I think, had a massively online course about zero-knowledge proofs. As I think 2 of the inventors of ZK proofs were here from UC Berkeley. Shafi Goldwasser and Don Song, I think, are both heavily involved in it. And I think they're on the original paper. And I really should have checked that before I said that. But, there's great resources out there. I'm happy to point you to them. If you think this is interesting, definitely take a look. All right, so in summary on the exotic primitives that we covered, we got VRFs, which is private randomness that's later publicly verifiable. We have erasure coding, so we're making data robust against losses. Shamir secret sharing, which is redundancy for your secrets. Proxy re-encryption, which is kind of authorizing access to your data, but with cryptography. And ZK proofs, which is just magic, but really expensive magic.